Hello everyone, welcome to ME269. My name is Muhammad Hamouda. I'm going to be the tutorial TA for this course, and in this tutorial we're gonna solve problem set number 1, which is related to the single phase electric circuit. So for problem 1, the voltage V0 in the circuit shown below is 30 voltage. Find I1, VG, and the power delivered by the voltage source. So the given is the voltage V0, which is the voltage across the 10 ohm resistor here. And it's required to calculate I1, which is the current passing through the 6 ohm resistor, and the voltage VG, which is the source voltage, and the power delivered by the voltage source, so the power delivered by this source. Okay, so first we need to calculate I1, which is the current passing through 6 ohm resistor. In order to calculate I1, we can calculate the voltage across this 6 ohm resistor, and then using Ohm's law we can easily calculate I1. But the given is V0, and V0 is not the voltage across 6 ohm resistor. V0 is the voltage across this 10 ohm resistor. So by using this V0, we can calculate I2, which is the current passing through this resistor, which is equal to V0 over 10. And then we can use a KVL in this loop to calculate V1, or just adding these 3 resistors in series, and using Ohm's law we can also calculate V1. After that, we can calculate I1 using Ohm's law, which is equal to V1 over 6. So this for the first part. Okay, so now we need to calculate the voltage VG, which is the source voltage. And in order to calculate the source voltage, we need to do a KVL in this loop. And in order to do that, we need to find the current passing through the 1 ohm resistor here and half ohm resistor here. We know I2, which is the current passing this loop, and the voltage V1 across 6 ohm. We know the value of I1 from the previous part. So we can do a KCL at this point in order to calculate the source current. Then the source current, IG, will be equal to I2 plus I1. After that, we can do a KVL in this loop to calculate VG. It should be noted here that this current IG is also passing through the half ohm resistor here. So this for the second bar. For the third bar, we need to calculate the power delivered by the source voltage, which is the power delivered by this source. The power equal to I squared times R in case we have a resistor, and is also equal to the current times the voltage. In this case, we know the voltage and we know the current passing through this source, so we can calculate the power delivered by this source by multiplying IG times VG. So that's all for this question. For question 2, given the circuit shown below, find each of the following. I3, which is the current passing through 3 ohm here, I6, which is the current passing through 6 ohm here, and then Vs, which is the source voltage. It's not the source voltage because this is a current source. This is the voltage across the current source. And in part C, we need to calculate the power dissipated in each resistor, then the power delivered by the 12 ohm source. So in order to solve this question, we need to remember the current divider rule. So if we want to calculate the current here, and we know the total current coming that will be divided into I3 and I6. So in order to calculate this current here, we should multiply the total current times the other resistor over the total resistor. So for I3, it will be 12 times the other resistor, which is 6, over the total, which is 6 plus 3. And for I6, we can do the same, 12 times the other resistor, which is 3, then over the total. Also, we can calculate I6 equal to 12 minus I3 using the KCL. Now we need to calculate the voltage across the current source. So this voltage is the same voltage across 3 ohm and the same voltage across 6 ohm because all of these elements are connected in parallel. So Vs is equal to I3 times 3 or I6 times 6. For the next part, we need to calculate the power dissipated in each resistor. So I told you that the power dissipated in the resistor is equal to the current times the current square times the resistor. So we have I3 squared times 3 or I6 squared times 6, or we can use the current times the voltage. So I3 times this Vs is the power dissipated in 3 ohm, I6 times Vs the power dissipated in 6 ohm. And finally, the power delivered by the 12 amp source. We know the current, we know the voltage across this current source, so we can multiply the voltage times the current to calculate the power delivered by this source. So that's all for this question. For question 3, using the node voltage method to find the power associated with each element in the circuit shown. So in this circuit, we have a voltage source, we have a current source, and we have resistances here. So in order to solve this question, we need first to know how many nodes do we have. So for this circuit, we have 3 nodes. We have one node here, so all of this is just one node. We have a node here and another node here. So we have 3 nodes. Then we should choose one node as a reference if it's not defined in the circuit. So for me, I prefer to choose a reference connected to a voltage source. So I will choose this node as a reference, because if I know that this is my reference, so the voltage here is 0 plus 20, which means that this point is 20 voltage. And if this point was a node, so I directly know the voltage of this node. So we have a reference here, we have V1 for this node and V2 for this node. So we have 2 nodes, and then we should write 2 node equation. The first one is for V1, so it will be V1 minus 20 over 5, which represents the current I1. Then V1 minus 0 over 80, which represents the current passing through the 80 ohm resistor. Then V1 minus V2 over 10, which represents the current passing from V1 to V2, not I2. Then all of this equal to 0, and then we can simplify this equation. For the node V2, we'll do the same. So we have V2 minus V1 over 10, which represents I2 in this case, plus V2 minus 0 over 50, which represents the current passing from V2 to the reference. Then we have 4 amp entering the node, so it will be minus 4, which is equal to 0, and then we can simplify this equation. So now we have 2 equations in 2 variables, and we can then solve these 2 equations to calculate V1 and V2. after we have the values for V1 and V2, we can calculate I1 and I2. I1 will be V1 minus 20 over 5, and I2 will be V2 minus V1 over 10. Now we need to calculate the power dissipated or generated by each element. So for the resistors here, the power will be dissipated. So for 5 ohm resistor, we know the current I1, so I1 squared times 5 will give you the power dissipated in 5 ohm. For the resistor here, we know the voltage across this resistor, which is V1 minus 0. So the voltage squared over 80 will give you the power dissipated in this resistor. The same here, we can solve the power dissipated. So I squared times the resistor will give you the power dissipated in this element. And here we know the voltage across this 50 ohm, which is V2 minus 0. So the voltage squared over 50 will give you the power dissipated in this element. Now, coming to the sources, we have a 20 voltage voltage source and 4 amp current source. And at this step, we don't know either these sources are generating power or one is generating and one is consuming. So in order to know, we need to come at each source and see the direction of the voltage and the direction of the current. For example, for this 20 voltage, this is the direction of the voltage from negative to positive, and the current is entering from the positive side. So this source, this current I1 is positive, so this is the correct direction for the current, which means that this source is dissipating or consuming power. Coming to the 4 amp source, of course this source will be the generating source because we should have a source, but let's do the same math. The voltage across this current source is V2 minus 0, and V2 will be the positive, 0 will be the negative, so V2 minus 0, and this voltage is positive, so this is the correct direction, and the current is generated from the positive side, which means that this is a source. And you can do the power balance equation to find that you are correctly determining which source is generating or which source is consuming power. So that's all for this question. Let's move on. For question 4, find the admittance ZAB in the circuit shown below. Express ZAB in both polar and rectangular forms. So we have this mix of resistances and reactances. For here, this XL and this one is XC. So we have a mix and we should calculate the equivalent impedance. For this problem, the problem is ready. The reactances are expressed in ohms, so which means that we have the impedance value actually. So we have the impedance value for XL and the impedance value for XC, for XL, and for XL here. So the problem is ready. So we can just do the math. So we have 4 impedances in parallel, and then we can add these 2 elements in series to calculate the total impedance. So we'll have 3.2 plus all these in parallel, then plus J2.4, and we can express this in rectangular and polar forms. For problem 5, in the circuit shown below, the voltage of the source is equal to 20 sine 10 to the power 4t, and the current source Is is equal to cosine 10 to the power 4t minus 60. Use the node voltage method to determine the values of V1 and V2. So we need to calculate the voltage V1 here and the voltage V2 across the source, the current source here. For this problem, we have a inductor here, capacitor here, inductor here. So we need first to calculate the equivalent reactances. And in order to calculate the equivalent reactances, we need to calculate omega, because for XL it should be equal to omega times L, and for XC should be equal to 1 over omega times C. So we need to calculate omega, and we know that omega is equal to 2 pi times the frequency if the frequency is given, but for this problem it's already given here. So because this is sine omega t, so this should be omega, so we have the value of omega, and then we should convert all these values to the equivalent ohm. So let's do that. So we can do this. We can calculate the equivalent ohm for this inductor and capacitor, and then these values are ready now. The only missing part in order to solve this circuit in the phasor domain is to convert the voltage source here to the equivalent phasor, and the current source here is to the equivalent phasor. And for the voltage source, it's equal to 20 and angle 0, because we do not have any phase here for the voltage source. For the current source, we have 1 and angle negative, this should be 30. This is not correct, it should be 30 as it's here. Okay. And now the problem is ready to be solved. So we can now define our nodes. So we have one node here as a reference. We have one node here which is equal to V1 in this example, because this is 0 and this is V1. So this node is V1 and this node will be directly V2, and we'll do the same steps as we did in the previous question, but for complex numbers. So we'll write the equation for V1. So it will be V1 minus 20 and angle 0 over 2 plus the equivalent x, which is J4. So it's 2 plus J4. We have V1 over 20, then V1 over x2, and this is the value for x2, and finally V1 minus V2 over 1 plus x3, which is J2. So this now first equation. We should write the second node equation for V2. So it will be V2 minus V1 over 1 plus x3, and then V2 minus 0 over 10, and finally negative is. So now we have two equations, and we can solve these two equations to calculate V1 and V2. But because the given is the voltage and the current in the time domain, we should represent these values in the time domain also. So this will be the value for V1 and V2. For this part here, it's multiplied times root 2. It should not be multiplied because the professor agreed to give you these values as RMS, not maximum. So this should be 16.075 and this should be 13.788. I will correct this in the problem set solution. Okay, so now before solving the next problem, we should do a quick revision for the bar triangle. So as we all know, the bar triangle consists of the active bar B, reactive bar Q, and complex bar S. And this is the angle phi, which represents the power factor angle. So the power is active or true or real power. We have imaginary or reactive power, and here we have complex or apparent power. So for the active power, it's equal to VI cosine phi. Be careful here because the voltage here and the current is only the magnitude, not the angle. So it's just the magnitude. The reactive power is equal to VI sine phi. And the complex power here is equal to B plus JQ, or it's equal to V times I conjugate. The magnitude of this vector here is the multiplication of the magnitude of V times the magnitude of I. So VI cosine this angle will give you the active power. This length is V times I. So VI sine this angle will give you the reactive power. But don't forget that the voltage here is complex. Is phasor. The current here is also phasor. And this is a very important equation that we will use it in many times in this course. And this power triangle could be lagging for inductive. So the power triangle will be in this direction. Could be leading capacitive. So the power triangle will be in this direction. And could be unity, which means that the power and S is the same. And we do not have any reactive power. Now, let's solve problem number 6. Given the circuit below, find I naught and the overall complex power supplied. So for the power triangle, we have 4 variables: the active power P, the reactive power Q, the complex power S, and the power factor angle. In order to define this power triangle, 2 variables are needed. So only 2 variables can define this power triangle. So for example, this load here giving the 2 kVA, volt M means S, so we have the magnitude of S, and we have the power factor. So we can define this load. Here we have the kilowatt and kilovar, which means that we have power, active power and reactive power, B and Q. Here we have 4 kilowatt, which means that we have B and we have the power factor. So only 2 variables are needed to identify the load. In order to solve this question, we should first calculate the complex power of each load. So for each load, we should calculate the S value. So let's start with the first load. We have the magnitude of this S, but it's still missing the angle, and the angle is coming from the power factor. So we have the magnitude and the angle from the power factor leading, which means that this S is negative, which means that this load is capacitive load. So we have the complex power for this load for the second load, it's already given B and Q, so B plus JQ is equal to S, but the Q value here is negative because this is a capacitive, so it will be 1.2 negative J 0.8. For this load here, we have the value of P and the power factor, so the B over the power factor will give you S, and then the angle could be calculated from the power factor. So now we have the complex power for the three loads. We can add these three complex power to calculate the total complex power and simplificate this circuit. So we can either adding the active power and reactive power, or just adding these complex numbers to calculate the total S. Now we have the value of the total S. So at this stage, we have just one load, which is the total load, and this load represents all these three loads together. So we have a source and one load, and this load is the total load. And this load represented by total value S, and we need to calculate I naught. Remember that the S value, the complex value S, is equal to the voltage times the current conjugate. Here we have the voltage across this load, and we can calculate the current using this equation. So the current will be S over V all conjugate, and then we can calculate the current. So that's all for this question. Okay, for this question, the voltage across the load is given in the time domain. We have two loads in parallel, load A and load B, and each load is defined again using two variables. For load A, we have the power, the active power P, and the power factor. For load B, we have the value of S and the power factor. It's required to calculate the apparent and the power factor for the combined load. So for the total load here, we need to calculate the apparent power S and the power factor. We need to find the source current IS, and then we need to calculate the power loss and the reactive power loss of the transmission line. Then we need to find the source voltage Vs. After that, we need to calculate the apparent power and the power factor of the source, so the apparent power here and the power factor at the source. Finally, we need to find the capacitor to be connected in parallel with the combined load in order to make the combined power factor unity. So we need to connect a capacitor here in parallel to these two loads in order to make the total power factor unity. So first, we need to define the complex power of each load. So we need to calculate the value of S for load A and the value of S for load B. So for load A, we have B and the power factor. So we can calculate S, which is B over the power factor. And we have the power factor, so we can calculate the angle, or we can calculate the reactive power from the triangle. For load B, we have S and the power factor, so we can calculate B and Q for this load. And then we can calculate the total value of S, so we can add B and Q, and then we can calculate the value of S and the power factor, which is B over S. So this for part A. For part B, we need to calculate the source current. Remember, the voltage across these two loads is given. So we can use the equation S equal to VI conjugate because the voltage is given. I believe this is a mistake, so it should be 220 and angle 0. So this should be a 220. So the voltage is 220. This 220, okay? So this is not 311. It's given 220. So this is the voltage. So the current is S over V all conjugate. So we can calculate the current. Then in order to calculate the power loss in the transmission line, so I squared times R is the active power loss. I squared times X is the reactive power loss. So I squared times R, the active, I squared times X, the reactive. Remember, this current is the magnitude. So the magnitude of this phasor. For part D, we need to calculate the source voltage. We know the load voltage. We know the current and the impedance. So we can do a KVL at this loop to calculate the source voltage. So just a KVL to calculate the source voltage. Part E finds the apparent power and the power factor of the source. Remember, the apparent power S is equal to VI conjugate. So we can calculate the value of S, and we can calculate the power factor from the angle of this apparent power using the power triangle. Finally, we need to calculate the value of the capacitor to be connected in parallel to make the combined load power factor equal 1. So remember this power triangle. So for these two loads, for the combined load here, we have P and Q and S. Now we are gonna connect a capacitor in parallel, and this capacitor will generate reactive power. So you will have a reactive power leading. So this is lagging and this is a leading reactive power. So this Q will be reduced to a new Q here, and then we will have a new S. Okay, in order to make it unity, which means that we don't need any Q, so this Q new will be 0, then we should have QC equal to Q old. So QC is equal to Q new, sorry, it's Q old minus Q new, it's a typo. And now Q new is equal to 0, so QC will be equal to Q old. And this QC is equal to V squared over XC. And XC is equal to 1 over omega C. So we will have omega times C times V squared. Omega is given. The voltage is given. And QC here, it's calculated. It's the old reactive power. So the only unknown here is a capacitor. So we can calculate a capacitor. Now for this circuit, calculate Vs. We have two loads and two impedances here, and the voltage across this load is given. So we can start by calculating the current passing through this load, I2. So we can calculate S, and S equal to VI conjugate, and then we can calculate the current passing through this load because we know the voltage across this load. This current I2 is passing through this impedance too. So we can use a KVL to calculate the voltage across this load, and then do the same again, because now we know the voltage here and we know this S. We can calculate I1. Now we have I1 and I2. We can do a KCL at this point to calculate the source current. And finally, we can do a KVL at this loop to calculate the source voltage. Okay, for this question, a factory supplied from a 240 voltage network has the following 4 major loads. We have 8 horsepower induction motor with 0.8 bar factor lagging, a heater rated at 500 watts, 10 100 watt light bulbs, a synchronous motor rated at 3 kVA. So we have this combination connected in parallel and supplied from a 240 voltage. First, find the total real and reactive power and the overall bar factor. Second, comment on the change in the magnitude of total current after replacing the synchronous motor with an induction one having the same active power but 0.8 bar factor lagging. So we will change this load with one having the same active power. This is not the active power, this is the S value. And we need to change this 0.6 bar factor lagging by to 0.8 bar factor lagging. So first we need to calculate the S value for each load. So we can calculate the S for each load. And then we can add this complex power to calculate the total complex power. And this total complex power, the real value is the total active, the imaginary value is the total reactive power. And we can use this angle to calculate the overall power factor. Now, and also we can calculate the total current, because in the second part we will comment on the total current. So we can calculate the total. Here I calculated the magnitude because I need just the magnitude, and I know that the magnitude of S equal to the magnitude of the current times the magnitude of the voltage. So we can calculate the magnitude of the current. Now we will replace the active power here, we will have the same active power 1.8 here with 0.8 bar factor lagging. So we can change the load now to a new one by calculating a new complex power for the fourth load. These three are the same, and we can calculate the new total complex power, and then we can calculate the new current, and of course the new current will be higher than the old one, because here we have 0.8 bar factor lagging, which makes the S value higher, and then the total current will be more. So the keynote here, by improving the bar factor, we can reduce the system losses because the total current will be less. Okay, so that's all for the problem set. In the next slides, you will see extra problems and the solution of these extra problems. These extra problems are not in the problem set. Please try to tackle these questions and try to test your knowledge by solving these questions. The answer is already posted. Okay, thank you, and see you in the Q&A session.